Hello friends. So today we are going to discuss questions from heat and thermodynamics, and these questions are from the year 2016. Three questions, and these three questions are from the advance. So the first question, it states that the ends Q and R of two thin wires PQ and RS are soldered joined together. Initially, each of the wire has a length of 1 meter at 10 degrees centigrade. Now the end P is maintained at 10 degrees centigrade, while the end S is heated and maintained at 400 degrees centigrade. The system is thermally insulated from its surrounding. If thermal conductivity of the wire PQ is twice that of the wire RS and the coefficient of linear expansion of PQ is 1.2 into 10 to the power minus 5 per Kelvin, the change in the length of the wire PQ is. So we are given that we are having two wires. This wire is our PQ, and there is other wire which is our RS, and they are soldered at the ends Q and R joined together, and it is said that each wire is having a length of 1 meter, and initially it is said that each wire is maintained at a temperature of 10 degrees centigrade, and then P, so initially we can say the entire system is at 10 degrees centigrade. Okay. Now P is still maintained at 10 degrees centigrade, but end S is heated to over 400 degrees centigrade. And thermal conductivity of the PQ is twice that of RS, and we have to find out the change in length of the PQ. Okay. So this is the basic premise of the question. And so we can say that we have our wires, and wires are PQ and RS, and each of length 1 meter, long at 10 degree centigrade. And later on we are given that our end P for the wire PQ is at a temperature of 10 degrees centigrade, and S of wire RS is maintained at 400 degrees centigrade. The relation between the thermal conductivity is also given. So we are given that thermal conductivity that is our K of our PQ is equal to 2 times of RS. and thermal expansion for our PQ is given. So we are given that our thermal expansion alpha of PQ is given to as 1.2 into 10 raised power minus 5 per Kelvin. And for RS is not given. We can discuss that part later on also. Okay. And we have to find out the change in length of the wire, okay, especially for PQ. Okay. So basically we can say we have to find out the delta PQ when the temperature is changed from at the end S from 10 degree to 400 degree centigrade. Okay. So in this case, we have to remember that end S is at a 400 degree centigrade and P is at 100 degrees 10 degrees centigrade. Therefore, the heat is going to flow from end S to the end P through the wire, and these wires are connected in series. Okay. Therefore, we can assume that this solder joint is having a temperature of T at steady state. Okay. We can just assume it that. So let me write that heat flows from S, which is a hot junction, to P, which is our cold junction. Okay. And we can also say that the solder joint which we call as Q, or we can say it is R, reaches steady state temperature T. So it means basically at a steady state we can say that the heat flow through PQ equals to the heat flow through RS. Okay. And for this heat flow we can use the Fourier law, and we can say that our Fourier law states that the heat flow through a system Q is equal to Ka delta T upon L, where K is our thermal conductivity, A cross-sectional area, delta T change in temperature at different temperature, L is the length. Okay. And so we can write this with respect to two wires. We can say that for wire PQ and so we are having Q at our T temperature and P is at our 10 degree centigrade. Therefore, we can write our Q for our PQ will be equal to K of our PQ. This is A area, we can assume that it's same because it is not specified otherwise, and this comes as our T minus 10 and divided by length of PQ. Similarly, we can write for our QR, sorry, not QR but RS. So we can say RS and our S, our R is at temperature T and our S is at a temperature of 400 degree centigrade. So we can say Q of our RS will be equal to KRS area, and this comes as 400 minus T upon length of our RS. and at steady state these should be equal. You can say at steady state our Q for our PQ should be equal to Q of our RS. So we substitute it, we get this as K of our PQ, and this comes as T minus 10 divided by length of our PQ is equal to K of our RS area 400 minus T length of our RS, and length we are having same in both cases and area is also same, and we are also given that K of PQ is 2 times KRS. So we can substitute, we get this as 2 K of RS T minus 10 is equal to K of RS 400 minus T, and this KRS cancels out, and now it is quite easy to solve. We can just open this, as 2T minus 20 is equal to 400 minus T, and this will be coming as 3T and 420. Therefore we can say T is equal to 140 degree centigrade. Okay, and change in length. Okay, now we are only interested in one wire, that is PQ, but for the other wire we can also calculate. It doesn't going to affect that much. So let us understand how the temperature distribution is going to take place. Temperature distribution. Okay. And for our wire PQ, and we can just draw individually wire PQ. So this is P and Q, and we assume that this X is equal to 0 and this is our X is equal to 1. Okay. And P is our at 10 degree centigrade and Q is at 140 degree centigrade. Therefore we can say the temperature distribution for the wire PQ will be equal to, let us call this as TPQ, and it is variable dependent upon X, will be equal to our 10 plus difference in temperature 40 minus 10 and X upon L. Okay. And we can write from here that our TPQ X will be equal to, this will be coming as our 10 and L is our 1, so you can say this will be 130 times X, and we have to remember that our X will be less than equal to 0 but greater than equal to, or less than equal to 1, greater than equal to 0. And similarly we can write for our this RS also. So we can say wire RS, individually we can write same way, the temperature of our RS dependent upon our X will be equal to, we are going to have our 140 plus this comes as 400 minus 140 divided by X upon L, and we get this as T of RS will be equal to, this will be 140 plus 260 times X, and here also the X should be greater than 0 but less than equal to 1. Okay. This is independent equation for our this wires. But we are only interested in the PQ. Therefore, we can write thermal expansion of the wire PQ. Thermal expansion of wire PQ, and we can write that our, suppose that is our delta L will be equal to alpha, and this comes as our T of x minus T naught time dx, and integral for the entire length. And here alpha, everything is given, T naught is initial temperature, so we are going to solve it for PQ, and we can write for PQ, we know that our T of PQ of x is equal to 10 plus 130 times x, and we are interested, we'll solve this part first. So we can write this as our T of PQ times x minus T naught, and that will be over 10 plus 130, and T naught initial temperature, that is our 10. This gives us 130 of x. Now we can just substitute in the integral. So we get this as delta L of our PQ will be equal to integration 0 to L, and we are having alpha for our PQ, and we get this as 130 times x, and we have a derivative of x. Length is equal to 1. So we get this as alpha of our PQ time 130, and integration will be our x square by 2, 0 to 1. Therefore, we can say that our delta L PQ alpha is given to us as 1.2 into 10 to the power minus 5 multiplied by 130 multiplied by 1 by 2. And this goes by over 65, and so this will be approximately equal to 0.78 into 10 to the power minus 3 meters. Or we can say that our delta L PQ will be approximately equal to 0.78 millimeter. So option A is correct. A is correct. Okay. Now in this case, we have not, you can say, not given or not considered that for the expansion for our RS, okay, because it was not required in the question itself. Okay, that's why we're not bothered about it. And even if we consider, then there might be certain, you can say, shift in the junction and the steady state temperature which we have used, or equation for calculation of steady state which we have used, we have considered that the fixed length for the heat conduction which we have considered. Anyways, this delta L is quite small, so we can say that the effect of heat flow is negligible. Therefore, it is not required for RS. Or straightforward, we can say that in the question, nowhere we were asked about our extension for our RS rod, therefore it was not given. Quite straightforward, we can say that also. Next question, it states that A metal is heated in a furnace where a sensor is kept above the metal surface to read the power radiated P by the metal. The sensor has a scale that displays log to the base 2 P upon P naught, where P naught is a constant. When the metal surface is at a temperature of 487 degrees centigrade, the sensor shows a value 1. Assume that the emissivity of the metallic surface remains constant. What is the value displaced by the sensor when the temperature of the metal surface is raised to 2767 degree centigrade? So first of all, we have to find out our power radiated, and for that we are going to use Stefan-Boltzmann law. Okay, and we have to keep in mind that the sensor is going to display a value of 1 when the temperature is 487 degree centigrade. So we start with Stefan-Boltzmann law. Stefan-Boltzmann law, and which gives us that the power radiated P is equal to our emissivity and Stefan-Boltzmann constant, area and temperature raised to power 4. And the sensor is displaying a value which is given denoted by log of 2 P upon P naught. Okay. So we can say that sensor displays some value, and that value is equal to log of 2 P upon P naught, okay, where P naught is a constant, might be some reference power. And it states that the value displaced by the sensor is 1 at a temperature of 487 degree centigrade. Therefore, we can say that at T1 487, that is our 760 Kelvin, sensor, the value displaced by the sensor is 1. So we can say this is equal to log of 2 P upon P naught. Okay. And for T2 we have to find out. And from the Stefan-Boltzmann law we can clearly see that because it states that emissivity is constant, so the area will be constant. The Stefan-Boltzmann law is already constant, so from where we can say that P is directly proportional to temperature raised to power 4. So we can say that power P is directly proportional to T raised to power 4. Now we have two temperature, so we can divide this into two parts, or we can simply cite in the form of ratio. We can say that our P2 upon P1 will be equal to T2 upon T1 whole raised to power 4, okay, because it says that this emissivity is said to be taken as constant. Rest of parameters are already constant. And so we can remodify this particular at temperature T1. So at T1 we are having 60 Kelvin, and we know that this particular value is equal to our 1. Okay. So let me write. So we are given that at T1, which is our 760 Kelvin, we know that the value is equal to 1, so therefore we can write log of 2 P1 upon P naught is equal to 1, because now we have taken temperature as T1, so that's why replaced T1 is proportional to P1. From here we can write P1 is proportional to T1 raised to power 4 and P2 is proportional to T2 raised to power 4. And if we solve this, we can say that our P1 upon P0 is equal to 2 raised to power 1, or we can say that our P1 is equal to 2 times P0. And we can write at T2, for which we are going to calculate, that is our 3040 Kelvin, and so we can say that value prime should be equal to log to the base 2 P2 upon P0. Okay. And we can express our P2 in terms of P1. So we can say that because we already know the relationship, so we can say our P2 is equal to P1 T2 upon T1 whole raised to power 4. And therefore, if we divide both sides by P0, we get this as P0 upon P2 upon P0 is equal to P1 upon P0, and this comes as a T2 upon T1 whole raised to power 4. And P1 upon P0 we know is equal to 2. So this comes as a 2 and T2 upon T1 whole raised to power 4. Okay. Therefore, we can write our value prime is equal to log of 2, and in place of this P2 upon P0 we can write 2 times T2 T1 whole raised to power 4. Okay. And we can just use our logarithmic. We can write this as log to the base 2 plus log base to the 2, and this comes as T2 upon T1 whole raised to power 4, and this will be our 1. So we can say our value prime will be equal to 1 plus, we can write this as 4 log base to 2, and we get this as T2 upon T1. We substitute our T2 upon T1 because both temperature we already know. So we get this 1 plus 4 log of 3040 divided by 760, and this ratio will be equal to 4. So we can say that it will be equal to 1 plus 4 log to the base 2 4, and which can we write 1 plus 8 log to the base 2. Once again we get this as 1 plus 8 because this is equal to 1, and giving us that the value read by the will be equal to 9. Okay. Next question. It was asked in the year 2016, and it states that a water cooler of storage capacity 120 liters can cool water at a constant rate of P watts in a closed circulation system as shown schematically in the figure. The water from the cooler is used to cool an external device that generates constantly 3 kilowatt of heat thermal load. The temperature of the water fed into the device cannot exceed 30 degrees centigrade, and the entire stored 120 liters of water is initially cooled to 10 degrees centigrade. The entire system is thermally insulated. The minimum value of P in watts for which the device can operate for 3 hours is, and specific heat of water and the density of the water is given to us. So basic figure is given to us. We have a cooler and we have a device. and we have to, we can say, so the device, the cooler is cooling the hot water and the cold water is further given to device, which is cooling ultimately this device. So this is a cyclic process and going on from device cooler and from cooler to device respectively for hot and cold water. And in this case, because the system consists of mainly our two components, other than the first component is of cooler, which we can as water cooler or tank also, and other one is the external device. So we can say that we have a system which consists of water cooler, which we call also a tank, and this tank contains 120 liters of water, and the initial temperature is of the tank is 10 degrees centigrade. So we can see its initial temperature is 10 degrees centigrade, and the cooling power, because it is given that it cools the water at P watts at a constant rate of P watt. So we can say cooling power is our P watts. Cooling power is P watts, which basically means that it is able to remove P joules per second heat from the water. Okay. So we can say that removes heat at P joules per second. That is basically the cooling power. And then we are having external device. First was our tank, and then we have our external device, and it says that it generates a energy of 3 kilowatt, or we can say 3000 watt or 3000 joules per second. We can say it generates 3000 watt, or we can say 3000 joules per second. And it is given that the temperature entering the device should be always less than or equal to 30 degree centigrade. That is a basic constraint on that. So we can write that our constraint so we have a constraint that water entering the device must have temperature. Suppose we write this as T input, it should be less than or equal to 30 degree centigrade, and this should be continuously for 3 hour operation, or we can say at all times, during 3 hours, because in the question it is specifically asking about the 3 hours, or we can say for 10,800 seconds. And rest of the things are you can say given to us. And second thing, we have to also keep in mind that the water is already at a temperature of 10 degrees centigrade, and the device, the water, the you can say the temperature of the water that is entering the device is 30 degrees centigrade. So the temperature difference between the two is only 20 degrees centigrade. Okay, that we have to keep in mind also. So we can say that temperature rise allowed, let us suppose that is delta T max will be equal to 10 minus 30, or we can say this as 20 Kelvin. Okay. So this is the maximum allowable temperature, that is about 20 Kelvin. And let us suppose the initial temperature, we call this as our T1. Okay. And this T in, we can just call this a T max also, because this is a maximum allowable temperature. And this basically is, in general, we can say that the energy will be generated during 3 hours should be balanced by the energy consumed during these 3 hours. Okay. So first of all, we are going to find out the total heat added by the device over 3 hours, okay, because it is also generating the heat. Therefore, we can say that total heat added by the device, total heat added by the device. So we can say this as QD, D stands for device, will be our H multiplied by T. Okay. And H is already given to us, which is we have 3000, so this comes as our 3000 multiplied by 10800, and we get our this heat generated by the device, that is QD, will be equal to, this will be over 32.4 into 10 to the power 6 joules, or we can write this as 32.4 megajoules. Now the initial temperature of the water is said to be 10, and maximum can be up till 30 degree centigrade. So we can say the heat required to raise the tank temperature from 10 degree to 30 degree centigrade. Heat required to raise the tank from 10 degree centigrade to 30 degree centigrade. And let us call this as QR. R stands for required, will be equal to over MC and delta T max. So we can say this as the Q required, QR will be equal to 120 multiplied by 4200, and difference is 20 degree centigrade or 20 Kelvin also. So this will be giving us 10.08 into 10 to the power 6 joules, or we can say 10.08 megajoules. So it means this is the maximum heat absorbed by the water without exceeding the temperature of 30 degree centigrade. We can say that this is the maximum heat the water can absorb without exceeding 30 degree centigrade, because this is the major constraint of the entire system. And now we are going to find out how much the heat will be removed by the cooler over the 3 hours. So we can say that heat removed by the cooler over 3 hours. So we can say this as our Q of the cooler will be equal to P multiplied by T, and this comes as P time we already know is 10800 joules. Now we are going to find out the net input to the tank. Net heat input heat input to the tank. We can call this as Q net will be equal to, we have this as Q generated, Q device minus Q cool, and we simply substitute the value. We get this as Q net will be equal to 32.4 into 10 to the power 6 minus P times 10800. Okay. And this Q net should be equal to our Q allowed, okay, or we can say Q required, okay, because if this balance is not maintained, that the heat required and our Q net, then the temperature is going to rise above our is 30 degree centigrade. Okay. So we can say that our Q net should be equal to our Q required. Q required. Therefore, we can say this is equal to 32.4 into 10 to the power 6 minus P into 1080800 is equal to 10.08 into 10 to the power 6. Now it is a simple calculation. We get this as P times 10800 will be equal to 10 to the power 6. We can take common, so this becomes a 10.08 plus 32.4. Sorry, not plus but minus. So we can say this is equal to 32.4 10 to the power 6 minus 10.08 into 10 to the power 6, and this comes as our 10 to the power 6, and this we can say 0, so this will be 2 and 3, so 0.3, and this will be over 2 and 2, so this will be 22.32, and therefore P will be equal to 22.32 into 10 to the power 6 divided by 10800, okay, and this will be approximately equal to 2067 watts. Okay, so this amount is required to be operated for 3 hours without raising the temperature of our above 30 degree centigrade. Okay, so this completes all 3 questions from 2016 advance. Thank you.